Okay, welcome to lesson 4 in module 1. Today we're going to be learning about the 5-number summary or measuring for center as well. So those are the two concepts that we'll cover in today's lesson. I will be uploading the recording here, and we will be revisiting the applet here for stats that we can use in order to find the 5-number summary if you do not have a TI-84. If you have a TI-83 or a TI-84, I also have directions in the notes. I'm going to go to the notes really quick just to kind of talk through the lesson, and then I'll link another example as well so that you can see how to create what we call a box plot. Before we get into that, let's talk about mean and median. So these are concepts that you probably have already learned about in past math classes, but the notation might look a little bit different. So I want to show you here that X bar is what I call that. That's going to be what we use for the notation for mean. So when I have a calculation down here, you'll see that X bar. In order to find the mean, what we do is we add up all the values. This is the formula here. But in a nutshell, we add them all up and then divide by the number of terms. So for example, this might be the number of pets that people have. And it looks like we have 7 people that said that they had blank number of pets, 2, 4, 4, 6, 7, 9, 10. Well, we would add up all those pets, divide by 7, and the mean number of pets would be 6. Okay, I'll talk about this whole idea of resistance in a little bit, but before I get into there, let's talk about median. The median is different than mean. The median is actually the middle value. So I have an example off to the side here. In order to get the median, what you would first have to do is you would have to arrange all observations from smallest to highest, kind of like we did in a stem plot, and then you would find that middle value. So in this one, it looks like we have 1, 2, 3, 4, 5, 6, 7. When we do that, there are 3 on either side of this value right here, so that's our middle value. So 7 divided by 2 is going to be 3.5. But what that really means is that 3 values in on either side, 3 values, that's going to be your middle number. If I had 8 values, then I would have 4 and then 4. So I would actually have to average the middle 2 values there. But here I don't have to. My median is 6. You'll notice that that was the same data set that we had up here. So we actually have a mean and a median of 6. That's not always going to be the case. In fact, that's kind of unique. But that right there is the mean and the median. So talking about these two values and where it comes to play in statistics, you have right here an entire thing that compares mean and median. But the biggest comparison that we'll make here is actually in our graphing. When we graph, if our mean and our median are approximately the same, like we had in this data set, what that will mean is that our observations are symmetric. If our mean is actually higher than our median, so maybe our median is 6 and this mean ended up being 9. If that's the case, then our mean is bigger, it's at the bigger numbers, so that would actually be skewed to the bigger side of the number line, which would be skewed to the right. If my median was 6 and my mean was, let's say 3, then it would mean that my mean is lower than my median, which means that it would be a skewed to the left distribution. The reason that that happens is because our mean is not a resistant measure. When you're counting in like this, I could add a 100 right here to the end. I could have 2, 4, 4, 6, 7, 9, and 100 in my data set. And it wouldn't matter. My median would still remain 6 because I just count into that middle value. So we call that resistant because it's resistant to anything happening on the outside. It's resistant to change. When I come to this one though, if I did 2, 4, 4, 6, 7, 9, and I change this to 100, I'm adding all of those values up and then dividing by 7. All of a sudden, this number is so much higher. I'm guessing in the 20s, 30s. So we go from it being 6, now all of a sudden it's in the 20s or 30s. So that right there shows you that our mean, because we're adding the values up, if I change just one of these values, it has a profound effect on the data. So that's where we say that the mean is not resistant to outliers. It definitely is affected by any kind of outlying values. So that's going to be a key component to where we move forward in here. Okay, so I'm going to talk briefly about the quartiles, and then I'm going to pop off of this video and show you an example of a box plot. So the quartiles, what we'll do for the quartiles and the 5-number summary, if we are going to use the median, if we're going to use the median as our measure of center. So namely, if we're using any kind of skew distribution to the left or to the right, you're going to want to use the median, and we're going to use what's called a box plot in order to actually graph it. So the quartiles break the values right into quarters, okay? So the way that our 5-number summary is going to work is we are going to have our Q1, our quarter 1 is going to be from the minimum value to quartile 1. That breaks the middle 25% of your data. The next one is going to go from 25 to 50% of your data. That's your second quarter of the data. Then we have 50 to 75 and 75 to 100. So that's how the quartiles will work. And that's how our graph will also work. I'm going to show you that graph in just a second, which is called a box plot. We make a box plot to really get into, the box is going to be the middle 50% of the data. When we have skewed data and there's a lot going on either sides, we have outliers here or outliers here that are causing this skewed distribution, we really want to just take a look at what that middle 50% of the data is. And that's what this 5-number summary is going to do for us. We have what's called a 5-number summary interquartile range, which means that middle 50% of the data, you take Q3 minus Q1, and that'll tell you how many values are in that middle 50%. And then we actually have our first test for what we call outliers. We take 1.5 times that interquartile range. We add that to Q3 and we subtract from Q1, and anything outside that range will be deemed an outlier. I'm going to show you all of that in the next video so that you can see this with numbers. But that is the 5-number summary and what we're going to be looking at in just a minute. The very last page here gives you another example of all of that, where I actually found the buildings in San Diego County. I found some buildings here and their heights. 500 is actually our tallest building. And so I put those building heights here, and I broke it down and I showed my work for the median. Then my quartile is halfway in between that. So the median marks the middle 50%. So there you go. There's your median, your middle 50%. And all I did was count in to find that middle value. I had to average this one because it happened to be in between those two. And then from there, your other quarter, you literally just count in there from your median to your minimum. That's going to give you your quartile 2. Your quartile 3 will be right in the middle of your median and your maximum. It'll be right in the middle. I had to average all those values just because of how many values we had in our data set. And then I made my box plot. This will make sense to go back and look at after we go through the example on the next video. So I'm going to end this recording now, and we'll pop over and look at an example of a 5-number